Okay, so we were here. So I suppose this was conveyed that what happened over here. I just uh, I had these guys which were not identities, and I replaced these eigenvalues by action of operators. So this Wi square I can get by acting with this operator twice, omega square, and over here I can this Wi by acting with operator omega hat, and this is just a number. Well, this wasn't square, and this I shouldn't write as omega square average. This was omega average squared. One has to be careful. Those two are different things. This is just a number, so I'm taking it in with the operator. So this, now what happens is all of them can be become identities. So I can do the sum, and this just becomes omega square plus, this is again omega squared times identity minus 2 omega hat, which is just omega hat minus omega identity squared. Right? So the uncertainty in this observable is square, which is the variance, is just the average value of this guy within your state, sandwich between your state. Whenever you sandwiching an operator between a state is called the average value. So it's the average value of this operator is the uncertainty. We will see its example. Maybe I shouldn't go to the example of this right away. Maybe let me make a few more comments and do a simpler example first. So this is comment 4. Now this is about stationary states. Suppose you have now, okay, you have this Hamiltonian. Remember what is Hamiltonian? It is the operator which appears in your Schrödinger equation. And why it appears in the Schrödinger equation? Because what is Schrödinger equation is just a statement that your time evolution is given by this unitary operator. So time evolution is always given by unitary operator. For small times, it's always can be written as action of a Hermitian operator, slightly away from the unity. And if you assume that the time evolution is such that at each step you have to apply this same u epsilon with the same Hamiltonian, with the same operator over here, then it exponentiates to this. This is all we showed last time. If this happens, then you say that this operator is time independent in the sense that this, suppose this is time, at each point you're using same u epsilon for small change from here to here. If not, then you imagine that all you are doing is that you are changing the operator you are using over here from time to time. But whatever you're doing, this is always true. So it could be that at each time you use a different operator over here. If not, if you always use the same one, those problems, you can just call it that this time, these problems have time independent Hamiltonian. These are also called time independent problems. Time independent systems of problems. Doesn't mean that nothing depends on time, just the Hamiltonian doesn't depend on time. So this operator, which appears in the time evolution, we know from here that has to be Hermitian. So H hat Hamiltonian is given a name Hamiltonian and it's Hermitian. So it can be an observable, and it turns out that it is indeed an observable. This observable is called the energy. You can take it as a name for now, but it's pretty much what our usual conception of energy is. It is exactly the same. We will see later that why it's energy, why we call it energy, but just take it as part of definition right now that whatever this observable is, it's called the Hamiltonian, and it's actually, you can give it another name, is the energy. So the eigenvalues of H are the possible energies that the system can have. And since H is Hermitian, so it will have a complete spectrum. Its eigenvalues will be real, as energies should be, and the eigenvectors will establish a complete set, complete orthonormal set. When I say orthonormal set, it means orthonormal, a complete basis. So that means I can write, just like for any other observable, I can write my any state as a sum, as an expansion of these eigenvectors. And I'm using E as an index. It could be continuous or discrete. I'm just schematically including both possibilities in this sum. If it's discrete, if the energies are discrete, you can obviously write something like this. Give it some name. I've put in E here just to indicate that this is the energy basis wave function, just the coefficients of expansion. It could sometime be that part of it is discrete. Well, actually it happens a lot of time. Part of it is discrete and part is continuous. So you start discrete and at some point you get continuous values. But continuous values, you can also think of them as, you can just discretize with a small spacing and think of all of them as discrete. This is essentially we have been doing. So in any case, I can expand my state in terms of energy eigenbasis, just like I can expand it in terms of eigenbasis of any observable. I can do it in this one too. Now let's see what does it say about the Shojanga equation. Well, first of all, if my state is one of starting state is one of the energy eigenstate, then what happens to this over time? I know that at a later t, this should be given by this action. But what is this action? This is just a power series in H, and any power of Hn on E is just e to the power n E, because I am repeatedly acting with H, and every time I just bring out an eigenvalue E. So this gives me a power series in E. So this has this psi, if I start with E at time 0, so this I can think of it as E at time t. So I started with E at time 0. After any other time, at any other time, it will be just E multiplied with this. But it's just a phase. And we know that none of the probabilities, if I have to compute any probability of any operator whatsoever, I'm computing average values or there are any moments. If I do this at t equals 0, or if I do it at t equals t, this phase will cancel out, because once I will get this, and once I will get this, so this will be give me 1. Not only the average values, but even the probabilities. Well, in any case, this time evolution is extremely simple for these guys. And if I compute any probability, let's say probability of some observable omega hat, it has its own eigenvalue spectrum. What is the probability of getting Wj in state E? Obviously, this is the formula. In my case, at t is equal to 0, it's E Wj mod square, and at a later time t, it's E Wj e to the iota E t over h bar mod square. So this is just a phase, so it drops out. That means these states, energy eigenstates, in energy eigenstates, so this is the best you can do in quantum mechanics. You ask about an observation, pick up its operator, and try to compute the eigenvalues of a certain outcome coming up. Try to compute the probability of a certain outcome coming up. Those are the most information you have in your states. In energy eigenstates, all the probabilities for any observation, for any observable, this omega hat was completely general, are time independent. So they do evolve with this guy, with this vector, but the time evolution is very, very simple. It's just with a phase, and an overall phase does not change any of the probabilities. This is just a general statement about quantum mechanics. If you have a state, you multiply it by a phase, none of the probabilities change. And this time evolution is exactly doing that, multiplying it by a phase, and that does not change any of the probabilities. So that's why this statement is given a short name, that energy eigenstates are stationary states. None of the probabilities change in energy eigenstates. Also, you can write this. So again, come back to this expansion. I can expand in my energy eigenbasis any state. Now, this is not an energy eigenstate. This is not a stationary state. Psi is any general, any arbitrary state. If this is at t is equal to 0, at later t, this would be e to the minus I t h hat over h bar acting on your psi. And what does it give you? So this goes and hits it. So in terms of energy eigenexpansion, if you know the energy eigenexpansion, then you know how the state would evolve. All you have to do is multiply the coefficients at later time with this vector. So finding the energy eigenvalues is equivalent to having solved the Shojanga equation because you know the time evolution once you have the spectrum. What do I mean by spectrum? I mean, once I know the eigenvalues and the eigenvectors, I can just expand any starting state in the energy eigenbasis by doing this. These will give me these vectors. And then I know at later times, they're just gonna get multiply with these phases. Now, these guys are not stationary. You can do it, you can compute, for example, this thing for any operator, or this thing. This is not an overall phase. It gets multiplied to some states and they are being summed. So you cannot pull it outside the psi. So these phases do not cancel. And in such a state, which is a linear combination of different energy eigenvalues, will not be stationary. Probabilities will change with time. However, probability of getting energy E in any state, because at any time psi at time t, well, let me write it this way. I know that if I start with time 0, it's A naught times, it can be written like this. What is the probability of finding energy E? So that's obviously this coefficient in the expansion. Mod square, which is actually time dependent. So the probability of getting a certain energy does not change with time. Others will do, but not of the energy. Energy is special in this sense. All of these statements I'm making when H is time independent. When H is not time independent, then none of this applies. Then you don't have stationary states, and the probabilities you just don't have stationary states, because at each time your Hamiltonian is different and it has a different spectrum. So at each time you will have to expand it into a new energy eigenbasis. And by using this, you can also write the evolution operator. U of t, which is, what was it? It was this. I can obviously do this. This is just an identity. So this gives me this, when this X on E picks up the energy. So this is actually a time evolution operator. You can do another thing. Let's say this is a new comment. Comment 5. Projecting the Shojanga equation. And for historical reasons, I told you that the Shojanga equation which we wrote, which, as I emphasized, is nothing except the statement that time evolution in quantum mechanics must be unitary, must be implemented through a unitary operator. And that unitary operator for small enough time must take this form. It has nothing to do with anything. It's just the statement that this operator is unitary. That automatically guarantees that this operator is Hermitian. And if this choice is same for every time, then this equation holds for all time. Otherwise, you just have a t over here. So it's not very deep, this equation, except, well, it's deep in the sense that it's telling you that the evolution must be implemented through a unitary operator. But it's not a condition which you could change. It's just inbuilt in the very basic framework of how you define probabilities in quantum mechanics. But for historical reasons, this is called time dependent Schrödinger equation. Doesn't mean that this age depends on time. It's just its name, because there's time appearing here. So it's called time dependent Schrödinger equation. We can project it, so it's written in abstract notation. We can project it into any basis we like on a given basis. So remember, we talked about this. If we have any statement, well, let's say mega hat giving you phi, these kind of statements we can project to a particular basis. This gives you psi of x dash. This gives you phi of x. Let's call it psi of x because there will be delta function which we have implemented. So this will be some action of operator in x basis which changes these components into the required components in x basis. So same thing we can do for Schrodinger equation. This is the equation, and let's just project it. So I have an operator acting here. I do this. So again, for emphasis, if you have any vector, if you know its components, you know it completely in any basis. Many a times people work in the x basis, but it's not necessary at all. Over here, I'm projecting it into x basis. So I make a statement about, what is this? This is just the components of psi along x. So this is just the wave function. We gave it this name today. So Schrodinger equation can be projected to the x basis and then it will tell me how the wave function changes. But it has complete information about how the vector is changing because wave function is defining the vector for me to this expansion. What happens over here? Well, this Hamiltonian energy can take different forms, but typically it's like this: kinetic energy, which is the momentum square over 2m, plus some potential energy, which is dependent on position. And our prescription is that momentum, this Hamiltonian, if classically, remember, this is what we wrote in our one of the postulates, that we replace x, if we are talking about position, is replaced by this position operator. And if we are talking about momentum, it's replaced by this momentum operator, which is just I h bar d by, which is just h bar k hat operator. And all the others, what you do is they are made up of, and classically they are made up of x and p. So you just replace these guys over here. So Hamiltonian would be this p hat operator squared over 2m. Typically, not necessarily always, but usually that's how you define energy. You have kinetic energy. So this is kinetic energy, and this is potential energy. Now, what is this? What does this give you? Oh, sorry. There's a x bar, psi. There will be a delta function which will be done through this integral, and you will have this square plus v x hat operator is just multiplication with x in the x basis. And this is just psi of x. So this gives you minus h bar square. Well, there's a 1 over 2m. So this is time dependent Shojanga equation in position basis. Similarly, you can project it to k basis, project to momentum basis. Over there, you can just check. I'm just doing it quickly. Because momentum, when you will insert a momentum eigenstate, this one, remember we had k hat. When k acting on this gives me this. In the k basis, k hat was just multiplication by k. So this will just give me h bar k square, which would be just p square, multiplication by just a number, 2m, which is the same p as appearing here. But for the v, instead of having just x, x will be replaced by whatever function I have for this. There's a difference of minus. Sorry. Now, because remember, we want this. This is part of our postulate. This must hold. And in x basis, this projects to this x being represented by x and p being represented by. If you compute this commutator, this just gives you this. I can check it quickly. Pick an arbitrary function. We are working in x basis. D by dx minus what is it equal to? Minus iota h bar x df by dx plus iota h bar. This derivative once x on x and gives me f of x, and once it x on f. So these two cancel and it's equal to iota h bar f of x. So that means this operator, which is a commutator acting on any function, gives me the function back multiplied with iota h bar. So I can say this operator has this commutation relation, or is equal to this. So if I choose p to be this works. And actually I'm not only choosing p, I'm just stating, I'm just checking over here, I'm just stating p is this, and I know that k takes this form. But if you are working in k basis, then I can either derive what is the expression of x. Actually we derived it in the beginning, that x had come out to be iota d by dp with a plus. We can check here that I want these operators to have this commutation. So if p is multiplication by a number p, then x hat should be chosen with a plus and with an h, d by dp, because this gives me minus so what is this? Again, once it kills the p, once it leaves it, and these two guys cancel, so I get iota h bar. So this commutator is equal to h bar, where x hat is d by dp and p hat is p. So that's what I have done in this projection, that you can project along momentum space, then this will just be a number, but this would be a operator. Most common is like how they write in elementary books to start with this, that this is the time dependent Shojanga equation. Can you hear me?
Yes,
Am I
sir.
connected? So what
Yes.
did I get disconnected like a minute ago?
No, sir, but the slides were like moving, तो मतलब नजर नहीं आ रहा था आप क्या लिख रहे थे, but we can
I
hear you.
thought it got disconnected for a second, but just for a second. Anyway. So this thing is called time dependent Shojanga equation. Shojanga equation projected to position space. Now I can, this fact that I have essentially solved the Schrödinger equation if I know the energy spectrum. And I said that at any time it would be E minus EET over h bar psi E, if with this boundary condition that at 0 time the expansion is this. So these are the coefficients at time 0 and they just get multiplied by this. I can project this, project to position basis. So I get and this gives me this wave function. This is just if I when I project my vector to position basis, this is called the wave function, but at some time t, at some other time t. and this gives me the energy eigenvector is components, the wave function of energy eigenvectors. And this is nothing except, if I take this, this I had been writing as E. Maybe I should write as E. And if I project it, so this would be the expression of H in X basis acting on some functions of X. So if I solve my eigenvalue problem in the X basis, those would be the functions which I will get will be exactly the projections of these vectors onto the X basis. How will I set up the eigenvalue problem in X basis? So I just take its expression in X basis, whatever it is. So if it's just p square over 2m plus v of x, then it will give me plus v of x this is an ordinary, in this case second order differential equation. Actually it's a Sturm-Liouville problem because it's an eigenvalue equation. Eigenvalue equation of a differential operator. But it's in the end it's just an ordinary second order differential equation, and which is a Sturm-Liouville problem where you have to solve it for this. It doesn't exist for all values of E, so you have to simultaneously solve for E and these functions. And you can do it. It's well known how to do these things. Well, not always is possible, but it depends on what V you choose. But this is an ordinary equation compared to what we had here. So if you look at this guy, this equation, this is not an ordinary equation. This is a partial differential equation. You have both differentials, partial differentials of x and t. So it's a partial differential equation, while this is a ordinary differential equation. But anyway, this will be useful in a second. If I put this thing in Schrödinger equation, this expression, what do I get? dt well, let me see, do I really want to do it? Psi of xt is equal to, it is this, there's no t over here, so brings down h bar multiplied with iota h e h. So this is equal to EE times E psi E of x. And on the other hand, so this is this side of the Schrodinger equation. From the other side, I have to apply this, which I have done over here. So it will give me summation E A E to the minus iota Et over h bar, and this h will act on these guys. And since I'm working in the position basis, this will give me psi E of x. And these two are equal because these two are equal. This is the Schrodinger equation. So what it tells me, well, it's again telling me the same thing over here, that this should be equal to in other words, you can say the same thing arguing from here, that if I can solve this, I have already solved the Schrodinger equation because I know how the wave function changes with time here. All I have to do is put in these guys here, and you have essentially solved the Schrodinger equation. But this is also essentially the logic of separation of variables. You have essentially separated the variable, and all you have to do is solve this, and you will have the solution for the total wave function. They will just be multiplied by these phases. And this thing, which is just the eigenvalue equation, for Hamiltonian, which is the NIG operator in X basis. But since it gives us a solution of Schrodinger equation, so this is also given again for historical reason another name. This is called the time independent Schrodinger equation. Okay, so any question so far?
No, sir.
Now let's take an example. Suppose you have a two-component system. What do I mean by that? This by definition means its Hilbert space is two-dimensional. So I can pick a basis, and I'm going to call the basis up and down. If you want, you can call 0 and 1. Anything you like. In quantum information, they like to call it 0 and 1. For the binary thing, you can take this to be off, this to be on. In any case, you have two vectors which are linearly independent, so you can build the whole space by linear combinations of these basis vectors. So these linear combinations where A, B belong to complex numbers, they have all the vectors, all the possible vectors in your Hilbert space. Now, what kind of operators I have, observables I have? Observables. I need Hermitian operators. Well, let me just make a comment. So what are these two states? We will do more careful physics later, but this could be, for example, why I draw it as up and down. This could be the z component of the spin of a particle. So particles, they spin. But it turns out, we will later see, that if I pick a direction, any direction in space, and call it z-axis. Z, again, as you can imagine, it's just a name. So you pick any direction. And for electrons, electrons have a property which is spin. So they are spinning like a top in some sense. And when you have a spin, the direction of spin, you have excess of spin and a direction. So it gives you an arrow. And you imagine that you can spin the electron in any direction. It's like literally like a ball. So you should be able to direct this spin in any direction. But it turns out that when you measure it along any certain direction, it's a projection. So you expect it can have any projection if it's spinning. But that's not true. It either has one particular projection, which is equal to h bar 2, or in the opposite direction. So it has only two projections, which are represented by this up and down along your desired axis. So this could be, these two components could be these two up and down states of an electron. They don't have to be. It could be that in an atom you are focusing on two levels. Atom can be on in this level, level 1 or level 2, two possible states of the atoms, two possible state of anything, of your circuit, anything you like. And I'm imagining they are linearly independent states. So Hilbert space is two-dimensional, and these vectors will describe everything there is to talk about the system. Now, what can we do with this system? The system will in general exist in a state like this, and I want to make measurements. When you make measurements, you want to make predictions about those measurements, and that will be related to Hermitian operators. So what kind of Hermitian operators are possible here? It's very simple in this case, that you can list all the Hermitian operators you can have. Well, first of all, let me give you a few. So obviously you have identity, which is Hermitian.
निगेशन हो जाएगा
Huh? You
सर
have
एक
this sigma z. This is not identity, but this is Hermitian. This is so maybe let me. This is called sigma z or sigma 3. Sigma 2 or sigma y. Well, sigma. Let's call it sigma 1. This is Hermitian. Zero. This is Hermitian. So all the, now you have, if you have 2 by 2, so why I'm writing 2 by 2 matrices? I have chosen a basis. This is the basis. So any psi can be written like this and can be represented then by a two column vector where A, B belong to complex numbers. And the operators, remember, they then take this form. Let's say you have an operator O, it will take this form. These are numbers, matrix elements. These are the most general, this is the most general operator you can write. And we have discussed it. If you give the matrix elements, or in other words, if you give these numbers, acting on this, you are defining an operator where these numbers are going in here. So operators on this Hilbert space are 2 by 2 matrices, and we want to pick the Hermitian operators, and we know that when you have Hermitian operators, then these matrices themselves become Hermitian. And Hermitian matrices, 2 by 2 Hermitian matrices, only have 4 real degrees of freedoms. So if I have built up, if I have picked up these 4 matrices, and you can show it very easily that they are linearly independent in the space of 2 by 2 matrices. So that's not the our Hilbert space. The space of 2 by 2 matrices is not our Hilbert space. Our Hilbert space is this one. A two component column. That's our Hilbert space. But I'm just talking about all possible Hermitian operators over here. I can write all possible Hermitian operators, any Hermitian operator, as alpha I summation I, like this, because they are, I know that the space of Hermitian 2 by 2 matrices is a vector space of 4 real dimensions, and in this vector space these guys are linearly independent. So any Hermitian matrix 2 by 2 can be written like this. But so this is not the convention. Convention is you put a minus here and plus here. Now I'm going to pick some special observables. So let's say you pick sigma 1, sigma 3, which is 0, 0, minus 1. And what are the eigenvalues? Well, it's a diagonal one, so eigenvalues are listed on the diagonal. These are 1 and -1. What are the eigenvectors? Well, they're so simple in this case. This is the eigenvector with eigenvalue 1, while this one is with the eigenvalue -1. So this guy is actually corresponds to this, because 1 is here, 0 is here. So it is this guy. While this guy corresponds to this state. So 1, 0 is the up, 0, 1 is the down state. Now, if you are in a general state, and you measure sigma 1, sigma 3, what is the probability that, well, I have to say that some numbers come out. Let's say when you measure this, you get +1. When you get this, you get -1. Right? Because I had these eigenvalues were +1 and -1. Eigenvalue of sigma 3 is 1, and eigenvalue of sigma 3 on this is -1. So when you measure sigma 3, what is the probability that you will get -1? So what would it be? It would just be b mod square. And what is the probability that you get +1? Is just a mod square. What would be the average value of the sigma 3 in this state? According to our average formula, it should be but this should also be given by sigma, which is up a star plus b star down ket sigma 3 acting on a up. This was bra, this is ket. So you have a mod square up plus a star b up, sigma 3 acting on down plus b star a down, sigma 3 acting on up plus b mod square down, sigma 3 acting on down. And you get a mod square. Sigma 3 acts on up, picks up a 1 and leaves you this. Picks up a -1 and leaves you this. Here it picks up a +1 and leaves you this. B mod square here it picks up a -1 and leaves you this. Now, well, I forgot to say something. I had defined a scalar product on it. The scalar product was that they are normalized. I have chosen the normalized states and they are orthogonal. Only then I could compute these matrix elements like this. So this normalization is there. So then this becomes 0, this becomes 0, and they give you 1 as using our other formula. Now suppose it's in this state, which I had assumed. And I make a measurement of sigma 3 and -1 comes out. What would be state after? What would be the state immediately afterwards? It will be this one. I haven't defined any dynamics on this, that how the state changes with time. So let me define it. Let me say that the Hamiltonian is given by, let me say, h bar sigma 3. I've just Hamiltonian is, it has to be a Hermitian operator, and I'm saying that the Hamiltonian is same as sigma 3. I've just scaled it just so that some of the formulas look even. Well, let me not scale it. Well, let me say it's proportional to sigma 3 and put an e here, some number e here. So what are the eigenvectors? Because since it's a scaling, they are the same as the eigenvectors of sigma 3. And what are the eigenvalues? This is e, and this is minus e. You can add an overall, well, let me just move on with this. I'll put that in homework. So if I have this, then if I start with state psi what would be the state after a time t? It would simply be this one. And the probability of getting -1 for sigma 3, it does not change because it was proportional to the energy.
Sir, we can't hear you.
You can't hear me? Can you hear me now?
Yes. आपने मुझे 2-3 लाइंस बोली हैं वो नहीं सुनाई दी.
Wait.
बट हमें तो आ रही.
अच्छा हो सकता है फिर मेरा कनेक्शन का मसला.
So probability for sigma 3 does not depend on time. But let me now consider another observable. So another observable. Let's say sigma 1, which is 0, 1, 1, 0. What are the eigenvalues? What are possible outcomes if I measure the observable associated with this operator? Well, to do that, I will have to find the eigenvalues. So determinant of minus lambda 1, 1 minus lambda equal to 0. So lambda square minus 1. So eigenvalues of this operator are also plus and minus 1. And what are the eigenvectors? This gives me B is equal to A. So a normalized eigenvector would be which is this one. It is normalized. Let me call this the plus vector. It's identified by this fact. It is normalized because if I do this, this gives me 1 by 2 up and up plus 1 by 2 down and down, and the other ones have these guys up and down and down and up, so they become 0. These give me 1, so they give me half and half equal to 1. And you can check, well, we have just found out that this guy has eigenvalue plus 1. So sigma 1, because of this formula, is written like this. It has a up down component plus down up, and they are both having 1 1 in front of them. So you can verify in this notation as well. This acting on plus is this operator acting on this guy. So when this hits this, you get a 0. But when this hits this, you get a 1, because down with down is 1. And you get 1 over under root 2 this. And when this guy hits this, you get a 1. But when this guy hits this, you get a 0. So you get 1 over under root 2. So it's an eigenvector with eigenvalue 1. The other eigenvector, well, maybe we should check, although I can get it directly, but let's check. So this gives me B is equal to minus A. And to normalize it, this is 1 minus 1 over under root 2. So I can write it and since these are eigenvectors with different eigenvalues of a Hermitian operators, and let me give it a name, minus. These are eigenvectors of a Hermitian operator with different eigenvalues, so they better be orthogonal, and you can check. So plus, when I flip it, it gives me the brass and 1 over under root 2 gives me the ket. Minus has a minus sign in between. So I get this with this gives me a 1. 1 by 2 times 1. This with this gives me a 0. This with this gives me a 0. But this with this gives me another 1. But with there's a minus sign. So they are orthogonal. Now let's ask this question. What is the, if I'm again starting with the state, my original state, which is at time equals to 0. What is the probability that if I measure sigma 1, I will get plus 1. So what would it be? It's just according to our rules. By the way, for this to work, I must take, otherwise I will have to divide by this, or it would be simply this if psi is normalized. So if psi is normalized, what does this give me? This gives me A star plus B star A plus B. This has to be 1. This hits gives you a 1. This hits this gives you a 1. The rest of them give you 0 because they are up going with down. So this gives me A mod square plus B mod square is equal to 1. So you must have this condition if you are going to use the simpler formula. So what's the, so suppose we have imposed this condition A and B are chosen this way. It's a normalized psi ket, which we will most of the time will assume. Then this probability is mod square is 1 over under root 2. The bra made out of plus, well, this one's the, one is up, one is down. And this dotted with A plus B and mod square. So when this goes with this, gives you A, and when this goes with this, gives you a 0. When this goes with this, gives you a 0. When this goes with that, gives you so that would be the probability. Quite different from the other one. And probability of sigma 3 minus 1, the only difference is going to be, it's going to give you this. Now let's ask some more, because we have the second operator, some more interesting questions. Well, first of all, let's answer this question. So at time t, what are the probabilities? So at time t, this changes to, I'm still using the Hamiltonian. Hamiltonian is this. Hamiltonian is same, but I'm observing psi1 at a later time t. So the state becomes this. And when I compute the probability, at time t, so I'm hitting again with these things, but this time I have these guys coming in. So this probability changes with time. Now let's ask another question. So suppose I measure the sigma 3 and get the value plus 1. So what will happen to the state? The psi will become the up state. And if what is the probability of sigma 3 being measured to be plus 1 again? If I measure it again, so the state has gone from psi to up. And if I measure it immediately right over here, the probability, this is now my state, of having plus 1 is up with up mod square, which is 1. So I'm 100% guaranteed that I will get the plus 1. What happens after some time? After some time, this goes to, since it's eigenstate with eigenvalue E, and this is after time t. So this is up. Let me give it a name. Let's call it phi of t. The up state I measured, found one for sigma 3 and waited for some time. Now if I find the probability of sigma 3 being 1, what is this? Does not change, still 1. Now let me do the following. I measured sigma 3, got plus 1. So the state goes to this one. If I measure sigma 1 in this state, what are the probabilities of getting plus 1 and minus 1? What are the individual probabilities? Well, probability of sigma 1 being plus 1 is plus with up mod square with up mod square. This gives you 1, this gives you 0. It's a half. Similarly, you can compute and as it should be because probabilities add up to 1. This is also half. So you are sure in this state that what would be the value of sigma 3 if you measure it? You are sure to get 1 with 100% probability. But in the same state, if you measure sigma 1, then you are maximally confused. You have 50% chance of getting one value and 50% chance of getting the other value. So you have uncertainty that what will turn up, and actually you have maximal uncertainty. You cannot tell, they are both equally probable. Now you suppose you go and actually measure sigma 1. Probability is half and half, but in an actual measurement you will get one of them. So suppose you measure and get the value -1 just by chance. What will happen to this? What is if you measure sigma 3 now, what is the probability of getting 1? Is it still 100%? Can you try to answer? Can someone answer? Are people even there?
I am here.
So what would be it? Would it be 100%? It was 100%. I had
Yes.
yes. Yes or no? What other people think? समरीन आपका क्या ख्याल है?
Sir, can you please repeat the question?
It's written over here. I was in state psi. I measured sigma 3. I got +1, so my state changed to this, up. In this state, the probability of sigma 1
Was half and half.
half and half. I measured sigma 1 and by chance I got -1 because I have to, in an experiment, I'll get only one answer. Now I again measured sigma 3. What is the probability of getting +1? Is it 100%?
I don't think so. It would be half and half, just like
Right.
sigma 1. Just a guess.
Well, what happens is since you measured and you got a -1, this was your state. But because of the measurement, you collapse. And you collapse to the eigenstate corresponding to this, which is -1. Now your state is -1. And if you immediately measure sigma 3 again, your probability of getting sigma 3 equal to 1 would be, this is the eigenstate of sigma 3, 1. It's scalar part with your current state, which has now become the minus state, corresponding to sigma 1 being -1. So it is this, and this is 1/√2 up minus down square. This gives me 0. This gives me minus 1/√2 mod square. So it's a half. So it's no longer 1. So you measured sigma 3, you found the value of +1, and then you know that you are sure if you measure it again, you will get +1. But if you measure sigma 1, that changes the state completely. You again become confused about sigma 1. Now you are sure about sigma, you again become confused about sigma 3. Now you are sure about sigma 1 because you just measured it. And it has become this state. So you know that now the probabilities of sigma 1 being -1 is 100%, and probability of sigma 1 being +1 is 0%. But this has changed the other probabilities. They have become half and half.
So, sir, why is that so?
It's just what your theory tells you. So you measure along sigma, this operator, let's say, if you think in concrete terms, the sigma 3 operator, you can say that you're measuring the spin along the z-axis, and sigma 1 is measuring the spin along x-axis. If you're sure about what is the value of spin along the z-axis, you are maximally confused about what is the value of spin along the x-axis. And when you become sure about what is the value of spin along the x-axis, +1 or -1, you become completely unsure about the value along the z along the z-axis. And if you keep measuring, you keep changing, you keep projecting to, so for example, you start from this state. I measured, I projected to this. I measured again, by chance I can project to this. I measured the other one. So here I measured sigma 1. Here I measured sigma 3. If I again measure sigma 3, I'll definitely get this. But if I measure sigma 1 again, I can get anything. Maybe by chance this. So they will keep changing. Another interesting phenomena which will happen is, so you measure sigma 3 and you get this. No, let's say you measure sigma 1 and you got minus state. What happens to it after some time? T. Let's say, let's call it chi t. Minus 1, I know how the up and down states evolve because those are energy eigenstates. So I can expand this thing. I know its expansion. It is this. So with time t, this becomes this has positive eigenenergy. So it comes Et by h. And the other one picks up negative energy. So that makes it plus. You get this. Now, if I ask, I measured sigma 1, I got this, I got minus 1, and I projected to this state, waited for time t. Now measure sigma 3 again. Well, in this case, nothing very interesting happens. It still remains 1 by 2. But let's say, okay, so you waited, now you measure sigma 1 again. What would be the probability? Would it be minus 100% for minus 1? So probability of sigma 1 being minus 1 at time t. What is this? It is just minus. This is your state. When you compute this guy is up minus down. And this is being dotted into up. So this can give me something. This gives me 1 by 2. And finally, I have to make a mod square.
Oh, okay.
So this gives me e to the minus iota et over h. This with this is not going to give me anything. This with this doesn't give me anything. This with this gives me 1 by 2 e to the iota et over h. So what does this give me? This is cosine et over h mod square. So if I wait for some time, I measure sigma I measured sigma 1, I got -1, but if I wait for some time, it doesn't stay -1. The probabilities are changing. They are sinusoidal. Because the evolution is to sigma 3 through this operator. So these eigenvalues, they don't have to remain constant with time. And the state keeps evolves like this. These are not the eigenvectors of sigma 1. So you get a changing probability, a sinusoidal kind of probability for measuring sigma 1. So sometimes you have full probability for having -1, sometimes you have 0, and sometimes you have in between. If you catch it at appropriate time, you will be sure that you will get -1. You will get -1. If you catch it at this appropriate time, you will be sure that you will not get -1. You will get +1. In between, you will not be sure. You will have different probabilities. But no matter where you catch it, so if I catch it here, if I measure it at this time, and I get -1 by chance, right after this moment, I will be sure to get -1 again, because it will forget about this evolution and collapse to this again and start from there again. So any question? I think I should stop here.
सर हमारे रिजल्ट का कुछ
आपके क्या?
सर रिजल्ट का नहीं बताया
रिजल्ट का बस मैं इस वीकेंड पे मैं उसको अपलोड करने की कोशिश करता हूँ.
ओके सर
और दूसरे कि मैं आपको होमवर्क दे दूँ.
जी सर दे दें
Right now, today I got the feeling maybe लोगों ने पिछला लेक्चर में देखा था कि people are kind of now lagging behind. Is it like fast or what? और आप लोग इसको भी फॉलो नहीं कर रहे?
सर एक साथ 3 घंटा बहुत हो जाता है.
Okay, so maybe we can do get 2 hours दोनों दिन कर लें
Yes,
बस.
yes, that is better. When one lecture in a go is too much.
Okay, let's do it 2 hours and 2 hours. ठीक है?
ठीक है.
ओके सर
कोई और किसी और का कोई कमेंट? चलें सही है.